Section 2.6 is on page 70, talks about exact and integrating factors. Theorem 2.6.1, you did this already in 5C, and I'll point that out. Let the functions m and the partial with respect to y of m, the partial with respect to n, the partial with respect to x of n, where subsequently denote partial derivatives, be continuous on some rectangle. So here we're talking about x being between some alpha and beta, and y being between some gamma and delta. So we're really talking about, if you could picture, something like that. Alright, and this is the equation right there. I'm going to rewrite this equation for you really quick. I'm going to put this on the side. And this equation I'm going to rewrite. This is dy dx, just to demonstrate. So this is m of x and y times dx plus n some x and y dy equals 0. So it's important for you to really write it this way, to know what m is and what n is, because the rest of the theorem talks about this equation is exact, is an exact differential equation if the partial of m with respect to y equal the partial of n with respect to x. So you're kind of doing backwards. If you could view it that way, that will be good. At each point of r, that is, there exists a solution phi satisfying the equation that phi sub x equal this and phi sub y equal n. If and only if m and n satisfy equation 1, well, I'm gonna really say, you did this back in the days, you called this f of x, y, if you remember, in which this right here was the vector field. So find a function f so that when I apply the gradient on it, I get the vector field from 5C. You called it not exact, you call it conservative. So here they call it exact. That's the equivalent of a conservative vector field. And we're going to really check the same way we did back in the days. If the gradient crossed with f equals 0, then f is a conservative vector field. And if it's conservative vector field, then what? We could find such a function. And what's del crossed with f? Del is an operator, partial with respect to x, partial with respect to y. And here I'm going to put them in order. M first. M is what with x, and n is with y. And if you do the partial, that's the partial of x minus the partial with respect to y of m equaling 0. And if you move this to the right hand side, you get exactly what they have. Easier than remembering what they have, but you do have to write it as sort of like saying, do you remember f dot dr? And f will be mn. Back then it was p and q, dotted with dr, which is dx dy. You really don't have to know all of this. I'm just trying to make this related to what you've done already, right? And if I start my first example, I was going to put all of that down here, but since we put that up there already, here we go. Let's start with some examples. If I look at page 75 in the book, it says determine whether each of the equation in 1 through 8 is exact. If it's exact, find the solution, right? Back then it says determine if the following vector field is conservative. If it is conservative, find the function f of x, y that satisfy the gradient of f equal f of x, y. If you remember that. I'm sorry, I got it backwards. The gradient of f equal the vector field. That's what you did back in the days. Well, let's see how this works. I'm going to say this is 2x plus 4y dx equal, what is with the equal, plus 2x minus 2y dy equals 0. So here I'm going to go ahead and say, well, let's see. If I take the gradient, right? If I could do what the book says and say, oh, let's just take the partial with respect to y of the I component. That's simply 4. The partial with respect to x of the j component. That's exactly what we did in 5c. That happens to be a 2. Those are not equal. This is not exact. Another way of doing this is for you to say, you know what? Let me check if I take del crossed with this function f, assuming f is and always in that order, right? Sort of the partial with respect to x. If that equals 0, it's conservative. Whatever you like, you could use, of course, 2x plus 4y. And here, I would use a 2x minus y. And this will be the partial with respect to x minus the partial with respect to y. That's negative t, which doesn't equal 0, so we say not exact. You could do that if you want. That's an ugly exact. Or simply not conservative. Whatever works. So, unlike calculus, in calculus they tied it down to its exact first, and after that they went ahead and dropped that condition. They just said find it, and you could do that. So, number 4, the same deal. If I really cross multiply, I'm looking at negative ax plus by dx equaling bx plus cy. And here, just like calculus, a, b, and c, all of these are constants. So if I move this to the right, I'm really looking at ax plus by dx plus bx plus cy dy equals 0. And if I go ahead and see if those are exact, well, let's see. If I take del crossed with f, so partial with respect to x, partial with respect to y, right, of ax plus by and bx plus cy, that would be the partial with respect to x, which is b, minus the partial with respect to y, which is b. That's 0. It's exact. So it did work. And how do you do this? It's up to you, just like we did back in the days. You could start anywhere you want. You could say f sub x equal, they like this phi. So you're trying to find phi of xy, or simply f of xy. You could use that if you wish. I really don't mind. I'm going to start with this equaling ax plus by. And if you recall, when I integrate, I am undoing a partial derivative. A partial derivative will be ax squared plus bxy plus some function. This book is going to use, let's go, g of y. If you remember, this is my answer. All what I have to do is find this and I'm done. And how am I going to find that? I'm going to say, if I take the partial with respect to y of this, that will be 0 plus bx. That must equal the j component. Those cancel out. So I do get that I dropped some. I'm sorry. Here it is. If I left out one small tiny piece, I'm like, hey, what happened? Plus g prime, which is now the derivative because it turns on one unknown. So g prime equals cy, and if I integrate with respect to y, g will equal cy squared over 2, and there it is. So my solution, phi of xy, or f of xy, is ax squared plus bxy plus cy squared over 2. And there it is. If you take the partial of this with respect to x, you should get that, and you take the partial with respect to y, you should get the other. Now, this is what they do here, though. They set this equal to k, and they let k always equal 0. So if you look at the equation will read ax squared plus bxy plus cy squared over 2 equal to k. They did that in calculus, and we couldn't explain it back then. I explained it to my class. my 5C class, by telling them what this is. It's a differential equation, and that's why they write the answer that way, but it doesn't matter. This is fine with me. I don't mind. The reason they write it this way, if you apply the partial on this, you will get the 0 right there. Alright? I want to do one more. And I leave the most fun till last. Look at this beauty. And if I look at this, again, if I take y e to the x y cosine of 2x minus 2e to the xy sine of 2x plus 2x multiplied by dx plus x e to the y e to the xy cosine of 2x minus, I forgot a y right there. So, now here, if I take the partial of this with respect to y, that will be the product rule right here. So this is a constant. It will be the cosine of 2x times derivative of the first times the second plus the first. Derivative of e to the xy is e to the xy times x minus, here, this is the only term with a variable, that's e to the xy times x, the sine of 2x plus 2. So, I'm getting here e to the xy times the cosine of 2x plus xy e to the xy times the cosine of 2x minus 2e to the xy times x, the sine of 2x plus 2. And if I take the partial of this with respect to x, here I have three functions multiplied. Derivative of the first will be 1 times the second plus the first times, if I take derivative of those two functions, derivative of e to the xy is e to the xy with respect to x times y cosine of 2x plus e to the xy. Derivative of cosine is negative the sine of 2x times 2. And of course, derivative of negative 3 is a 0. So this is e to the xy cosine of 2x plus xy e to the xy cosine of 2x plus minus x times 2 e to the xy x sine of 2x, and as you see, they check identically. I know you were hoping that this doesn't check. Well, it does. Now what? Now that I know this, I'm going to start with my solution. I'm going to say, well, let me start with this. I'm going to start with phi sub y because that looks easier. Phi sub y equal x e to the xy cosine of 2x. And if I integrate, remember I'm undoing a partial derivative with respect to y. Phi, which is my solution that I want, will be, this is the only variable as far as y is concerned, xy. When you take a derivative, you multiply by x. When you integrate, you divide by that, plus a function of y. Well, find this g of y, and you're done. And let's see how that works. If I take the partial of my solution with respect to x, that's the product rule. That would be negative twice the sine of 2x times e to the xy plus the cosine of 2x times e to the xy with respect to x times y plus g prime of y. And since it's really lengthy, I'm going to put it here so we can see it all on one line. That should equal the I component. That should equal y e to the xy cosine of 2x minus 2 e to the xy sine of 2x plus 2x. And I noticed that this and that cancel out, and this and that cancel out. I'm left with g prime of y equaling 2x. And if I integrate, remember I'm doing a partial derivative. Oh, when I took a derivative with respect to y, that would be a function of x. My mistake. I get so used to the same thing. So this would mean g of x actually equal x squared. Replace x squared in there. And my solution to this equation would be phi, or f of xy, is actually e to the xy cosine of 2x plus x squared equal to k, or 0. Take a partial with respect to x, you'll get this. Take a partial with respect to y, you'll get this. And that will be the solution. It should be, the reason there's a k, this should be plus a constant. They always set that equal to 0 in this section. So either see this or you see it equal to 0, makes no difference. Let me give you the homework on this, and we're just going to do 1 through 7 odd.